So this lecture is about vector addition using components. So in the last lecture we learned how to break a vector up into each of its components into an x and y component, and how the x and y components can be seen as being two vectors that when added together have a resultant that's equal to the vector that you're breaking down into components. Now in this lecture we're going to see the usefulness of that and why it is extremely useful and a great method to use when adding vectors together. So I'm going to have three vectors that I want to add together. I'm going to pick three force vectors, and one vector will be 25 newtons at 10 degrees north of east, and for the purposes of this we'll assume that these angles have two sig figs in them. Another vector, another force is acting, and it has a magnitude of 30 newtons at an angle of 70 degrees north of west, and then a third force is acting. It has a magnitude of 40 newtons going directly south or straight down. So physically what this would represent, say that we have an object in the middle, it could be a rock, or any object, and there are three forces acting on it. What we would ask is, what is the net force acting on it? In other words, what force would the object actually feel? It wouldn't feel three separate forces, it would only feel one force, and that single force that it feels will be the result of the addition of these three force vectors. It would be, in other words, the resultant of these three vectors. So we will use components to add these three vectors together and find out exactly what force that object that these three forces are acting on will feel. As before, we need to define a coordinate system, so I will define to the right as being positive, and I will define up as being positive as well. And what we need to do is we need to take each of these three vectors one at a time and break them up into their x and y components. So let's start with a 25 Newton vector. We take the 25 Newton vector, which again is pointing at 10 degrees north of east. We'll break it up into its x and y components, and so the x component points to the right and the y component points up. Nice right angle there. And so our y component will be the sine of 10 degrees times our hypotenuse, 25 newtons. So that gives us 4.34 newtons. And I'll put a line underneath the 4 to indicate that it's not significant, but we're going to carry it through this calculation. The x component for this will be the cosine of 10 degrees times our hypotenuse, 25 newtons, and that will equal 24.6 newtons. We then go to the 30 Newton vector, which is pointing up and to the left, 70 degrees north of west. It will have two components, an x component that points off to the left, and a y component that's going to point up. So our magnitude here is 30 newtons. So let me backtrack a little bit. I'm going to call this xc1, yc1, because that was the first vector we used. It's always a good idea to distinguish between the different components. So this will be xc2. Now because it is pointing to the left, we have to make sure that we make it negative, since right is to the positive, so I'm going to put a negative in here for that reason. So negative cosine of 70 degrees times 30 newtons, which would give us negative 10.3 newtons. And for the y component, the second y component, that will be the sine of 70 degrees times 30 newtons. And so this will be 28.2 newtons. This is positive because the y component is pointing up. And then our last vector that we have is the 40 Newton vector going down. And because this is all in the vertical direction, it's all along the y-axis, we can say essentially that this x component will be equal to 0 newtons. It doesn't project along the x-axis at all. Whereas all of it is on the y-axis, and we would say that yc3 would be negative 40 newtons. Again, we have to say negative because we defined up as positive. Therefore, down has to be negative. So now we have x and y components for each of these three vectors. Now we're going to use a property of vectors, and we're going to say, okay, we want to add these three vectors together. What I can do is I can add all the x components together, and I can add all the y components together, and I can do it just like it was a normal arithmetic problem, because the x components are all pointed along the same axis, and the y components are pointed all along the same axis. So I no longer have to worry about the angles between them, because the angle is either 0 or 180 degrees. And it turns out that the addition of all of these x components of these three vectors turns out to be the x component of our resultant, of our net force that we want. So I will take the first x component plus the second x component plus the third x component, and that will give us the x component that our resultant would have. So I'll take 24.6 newtons plus negative 10.3 newtons plus 0 newtons. Again, note that negative, that doesn't go away, so make sure you include it in your calculation, which gives us the x component of the resultant being 14.3 newtons, and I'll keep on carrying that extra figure in there. The y component of our resultant will be the sum of the y components of each of these separate vectors. So this will be yc1 plus yc2 plus yc3. So we have 4.34 newtons. Okay, we get that from up here. Plus 28.2 newtons. Plus negative 40 newtons. Again, don't forget about that negative. And this will give us negative 7.46 newtons. All right, so this is the x and y component of the resultant force, of the force that results from those three forces added together and acting on that object. So now what we got to do is we're going to take these components and we're going to use them to figure out what the resultant is, what that resultant force is. We're going to keep our coordinate system in mind. So the x component, since it's positive 14.3 newtons, that will have to point off to the right here, and it'll have that magnitude. And then the y component, because it's negative, will point down, and as soon as I draw a vector down, I'm taking into account the negative, so you don't have to include it in there. And the resultant force of these two, okay, is the hypotenuse of this triangle. So I'm going to call this the resultant force. And I need to know two things about that resultant force. I need to know what its magnitude is, and because it's a vector, to be totally correct, I need to know the direction that it's pointing in. Okay, to figure out the magnitude of that force, I'm going to use the Pythagorean theorem. And I'm going to say that I know that the magnitude of that resultant force is equal to the square root of 7.46 newtons squared plus 14.3 newtons quantity squared. If you take that square root, and you would get 16.1 newtons. That is an extra sig fig there, so we would say that the resultant force has a magnitude of 16 newtons. Now if that's all we said, we wouldn't have completely answered the question of what the resultant force is, because I need a direction as well. So to get the direction of this force, I'll use right angle trig, and I'll say that the inverse tangent, because this is the angle we want, the inverse tangent of the opposite side, 7.46 newtons, over the adjacent side, 14.3 newtons, will be equal to theta. And so theta is equal to 28 degrees, to our g sig fig limit, 28 degrees south of east. And that is the answer to the question. So those three forces, 30 newtons plus 25 newtons plus 40 newtons with their respective angles, add together would produce a force of 16 newtons, oriented at 28 degrees south of east.